Hello guys, nice to see you. How are you doing?
Good afternoon. I'm fine.
Nice. So first, I think I would like to mention that our next lecture is planned on Friday. However, I got to know that need to attend a meeting with Institute of Nuclear Physics in Almaty. Hello guys, nice to see you. And the meeting is on Friday, so I will be busy with traveling and with the meeting. So we will postpone this lecture on Sunday. That's only one option to do it when I'm already back and you guys don't have other lectures. I understand that it may be not convenient for some of you, but those who will not be able to attend this lecture on Sunday, it will be recorded and available online. So you will have a chance to go through it. So we will consider simple harmonic motion with some damping. So that will be the main topic of our discussion during that lecture. And I will send you today an email with a Zoom link to this one postponed lecture. So we don't miss anything and still have a chance to discuss it. Okay, so I believe with a message who just joined now that I have to attend a meeting in the Institute of Nuclear Physics in Almaty on Friday. That's why our lecture on Friday will be postponed on Sunday. Those who will not be able to attend on Sunday, this lecture will be recorded as all others. So will be available for you guys to check later for your convenient time. Now I would like to recall you our previous discussion. So we introduced this concept of simple harmonic motion. We considered this ideal frictionless system spring block with certain mass. And based on that, we had a differential equation, like second order linear differential equation, solved it, got the solution for x displacement as a function of time. And then by taking first and second derivatives, we got the expressions for the velocity and acceleration as functions of time. For simple harmonic oscillator means some particle which undergoes simple harmonic motion. Now we will proceed further with the analysis of this system, and in particular, it will be the mechanical energy, kinetic plus potential energy of simple harmonic oscillator. And then we will consider some other systems which also undergo simple harmonic motion, which is simple and physical pendulum. So we will derive equations for their motion and like periodic motions. And we will see that they are actually also simple harmonic motions because we will get similar format of differential equation, the same type. So it will possess the same type of solution while we will operate with different terms because for a spring block, we were operating with position x, like the displacement. And for pendulum, we will operate with angle theta, like the deflection of pendulum from its equilibrium condition. However, the general format will be the same, and it will describe simple harmonic motion. So with this, let us change to the slides, and we start with the discussion of the energy, like mechanical energy of the simple harmonic oscillator. We remember expressions for velocity. Maybe let us write it here. Let's say for position x, it was a times cosinus omega t plus p, some phase constant. Then for velocity, we got omega a times sinus omega t plus p. Yeah, and here was minus. So we have these expressions which describe position and velocity of single harmonic oscillator. And we can now write expression for the kinetic energy. Let's say kinetic energy of the simple harmonic oscillator will be 1/2 mass of the block times its velocity square. And that can be written as 1/2 mass times omega square times a square times sinus square omega t plus p. So this is the expression for kinetic energy as a function of time. Also, we can do this for potential energy, and potential energy, obviously, it will be potential energy of the string. We remember that potential energy of the string is given as k, constant, string constant, times displacement squared divided by 2. So we know x in terms of amplitude and angular frequency. So kind of x dependence on time. So we can substitute in this equation, and we will get expression for the potential energy as a function of time of simple harmonic oscillator. So 1/2 k times x squared, that will be 1/2 k times a squared times cosinus square times omega t plus p. So we have expression for kinetic energy and potential energy as functions of time. Now we should recall that omega angular frequency from our previous discussion, it was given as square root of k divided by m. So if we substitute now omega square by k divided by m, let us do it for kinetic energy, it will be 1/2 m. So instead of omega square, here we put k divided by m times a square times sinus square omega t plus p. M cancel out, and we have 1/2 k times a square. So we see that this prefactor before sinus is the same as this prefactor in potential energy before cosinus. So now we can write the expression for the total mechanical energy of this system, so the sum of kinetic and potential energy. That will be equal to since these coefficients are the same before cosine and sinus, we can take them out from parentheses. That will be 1/2 times k times a square. And in parentheses, we will have sinus square omega t plus phi plus cosine square omega t plus phi. So I'm sure that you have seen many times the expression in the parentheses. This one, do you know what it's equal to?
It's equal to 1.
Yes, exactly. It's equal to unity. And that means that we get rid of time dependence. There's no time dependence anymore. It will be equal, like total mechanical energy will be equal to 1/2 k times a square, and that is a constant. So means that the total mechanical energy doesn't change with time for this ideal spring block system without any dissipation of energy. And what is important that this total total mechanical energy is equal to the potential energy of the string at maximum displacement, which is amplitude value of the displacement A. So that is quite convenient to know this fact, because we can use it for our convenience in solving some problems when we need to determine, for instance, velocity of a simple harmonic oscillator when as a function of displacement. So let us take this into our consideration now, this case, and we can write that total mechanical energy is equal to kinetic energy plus potential energy. That is equal to 1/2 mv squared plus potential energy of the string, be 1/2 kx squared, and that is equal to some constant 1/2 a squared. So from here we can express kinetic energy 1/2 mv squared is equal to 1/2 k a squared minus 1/2 kx squared, and express velocity as a function of displacement. Since we have periodic motion, there will be two solutions. It will be plus or minus, because it depends in which direction it will move. Either it's in the left side from equilibrium or in the right side from equilibrium. Square root of k divided by m a squared minus x squared. We remember, we already mentioned it today, that angular frequency is equal for this system spring block is equal to k divided by m. So that is why we can write that velocity will be equal to plus minus omega square root of a square minus x squared. So quite simple equation, and doesn't require any integration of this time and x dependent force like spring force. It all just based on the fact that total mechanical energy of a simple harmonic oscillator is constant, and that is equal to the potential energy of this at the maximum displacement. So if we consider some extreme points. For instance, let's consider x equals to a. We see here that a squared and minus a squared, it will be 0. And velocity obviously will be equal to 0, which makes sense. If we push to the extreme point, like maximum displacement, then kinetic energy will be equal to 0, and all energy will be defined by potential energy. So if we put x equal to 0, then we reach the maximum velocity, v equals to omega times a. And in this case, all mechanical energy will be defined by the kinetic energy of this harmonic oscillator. So with this, we can move further and consider the simple pendulum. So that's interesting system which can be used for determination, like measurement of the acceleration of free fall, and we will discuss it in more details. So simple pendulum is like consists of some rope with attached mass to this rope. Length of the rope should be much bigger than the physical dimension of the mass, and mass of the rope should be much smaller than the mass of the object attached to it. So it is fixed in some point, and this system can perform some periodic motion along some circular trajectory. And here is equilibrium condition. So when this angle theta is equal to 0. So now obviously this pendulum is not in equilibrium condition, and we would like to consider forces which act on this mass. So here is the weight mg. Then we have some tension here in the string, in the rope tension. And we can split this force, like weight, in two components. One component will compensate the tension in the rope. So this will be, this angle theta will be also here. It will be mg times cosinus theta. And another component, so-called tangential component, will be trying to push this pendulum into equilibrium condition, and this tangential force will be mg times sinus theta. Taking into account the fact that this tangential force always wants to put the pendulum into equilibrium condition, so it will change direction depends where this pendulum will be located. We can consider it with sign minus mg times sinus theta, because it always wants to put the system in equilibrium condition. And that will be equal, according to the second law of motion, mass of the pendulum times tangential acceleration, since this is the tangential force. That acceleration can be expressed in the form of second derivative, d square s over dt. So s is the path, dt squared is the path along this circular trajectory while pendulum is performing its periodic motion. So this s, the path, can be expressed as the product of the radius of the circular trajectory, and that is the length of the pendulum L times angle theta, which is in radians. So now we can consider that S here in this derivative is represented by L times theta. L is constant, the length of the pendulum doesn't change. That's why we can write that minus mg sinus theta is equal to m times L d square theta over dt square. So as you see, instead of x displacement in the system string block, we or pendulum operate with the angle theta, which defines how much our pendulum is deflected from the equilibrium condition. So now we can cancel this mass, and we can rewrite it in the following form. So it will be d square theta divided by dt square plus g divided by L times sinus theta. That is equal to 0. So there is one more thing we need to mention here. If we consider small deflection from equilibrium, means that theta is smaller than 0.2 radians, which stands to about 10 degrees, we can write that sinus theta for such small angles is like close to just theta. And that will help us to simplify our differential equation. So we can, instead of sinus theta, substitute just theta. But assuming this limits that we don't go too large values of theta. So in that case, we have d square theta divided by dt square plus g divided by L, and times, instead of sinus theta, we have theta. That is equal to 0. So we have this differential equation, which is second order linear differential equation. And the question is, do you remember where we saw similar type of equation?
The last time?
Exactly. Last time we had exactly the same equation, but just with respect to x, the displacement. So it was dx squared, d square x dt square plus it was k divided by m times x. That was equal to 0. So we have the same type, but just different terms, displacement and angle, but the differential equation is actually the same. So as we remember from previous time, in order to solve such equation, we first get the characteristic equation, and the characteristic equation for this type of differential equations will be lambda square plus, in our case now it's g divided by L, and that is equal to 0. So some of you guys asked me why we don't put here in the characteristic equation anything when we have just function theta or x. So the thing is that these types of equations the general solution is represented in the form, let's say x is equal to some constant times exponent lambda. So lambda is this parameter in the characteristic equation times t, for instance, some independent variable. We have time here. If we take derivative of this general solution, like first derivative, dx over dt, that will be lambda times c times exponent lambda t. And if we take second derivative, d square x dt square will be lambda square c exponent lambda t. So we see that here for first derivative we have lambda, for second derivative we have lambda square in front of the exponent function. And next to original function x, we don't have any lambda. That's why when we have here just x, we don't take anything in terms of lambda. So it's just coefficient next to x. And when we have first and second derivative, we take lambda and lambda square. Since we don't have first derivative here in this equation, we have only second derivative, we have lambda square plus this coefficient equals to 0. And then we need to solve this characteristic equation and get solutions for lambda 1 and lambda 2 and see which form these solutions are. It's either two real values or some complex values. So all these things should be taken into account in order to figure out in which ultimate form the solution of this differential equation will be. But again, this for simple pendulum differential equation is the same as for the string block system, and that's why we will not repeat our consideration in details here, because that's exactly what we have already done previously. We will just write the final equation, which gives us theta as a function of time. So we will have some theta maximum, which amplitude value of the deflection of this simple pendulum from equilibrium condition, times cosinus omega t plus phi. And here we need to highlight that this omega is equal to square root of g divided by L, as opposite to the string block system when we had omega equal to square root of k divided by m. So taking this into account, we can also express period of this periodic motion of the pendulum, and that is 2 pi divided by omega. That is 2 pi times square root of L divided by G. And obviously frequency of such a periodic motion will be angular frequency divided by 2 pi. That will be 1 over 2 pi times square root of G divided by L. What is important here that all these parameters, they are actually related to each other, but the frequency, angular frequency of the physical pendulum does not depend on the mass attached to the rope, which is kind of interesting. But indeed, we have only two factors which define the angular frequency or like period of this periodic motion. it is acceleration of free fall and length of the pendulum. Of course, that is true, assuming that theta is not large, because we made this substitution instead of theta, instead of sinus theta. If we take a closer look to expression for the period, and that's period, that's what we can easily measure. We can just measure time when, let's say, 10 full cycles of this periodic motion happen, then divide this time by 10, we will get with quite high accuracy the period of this oscillation. And we take E square is equal to 4 pi square times L square divided by G square. So our L, length of the pendulum, we can also measure quite accurately. So from here, we can express G. Sorry, it's actually not square here because we have square root. So G is equal to 4 pi square L divided by T square. So as you see, both length of the pendulum and its period can be measured quite accurately, and that's why we can determine the acceleration of free fall by using such mechanical system. Next step of our consideration will be physical pendulum. So not all pendulums are so well defined as a simple pendulum. When we can consider some mass as a point, like some particle attached to a massless rope. So this is some ideal system. However, in real life, we can have some solid, some rigid body with random shape. If it's attached in one point about which it can rotate, and this point is not located in the center of mass, then this body will also undergo some periodic motion if we disturb it from equilibrium condition, and then because of the gravitational force acting on the center of mass, it will undergo some periodic motion. So that this kind of system is considered as physical pendulum. And what is nice, it also follows these similar equations. However, it's a bit more complicated than simple pendulum, and we would like to discuss this in more details here. So let us go to next slide and consider some arbitrary shape rigid body. So let's have some point O, and this is where this body is fixed, so it can rotate about this point. And we have some point here, which is like stands for the center of mass of this body. So now this is distance d from the center of mass to the point about which the rotation can happen. This is angle theta, which shows how much our rigid body is deflected from the equilibrium condition, because equilibrium condition would be when center of mass is on this vertical line. And obviously here, this distance, it will be d times sinus theta, that will be the arm of force mg, which acts on the center of mass with respect to point O, about which the system can rotate and perform this periodic motion. So we can write that the magnitude of the torque of this gravitational force exerted to the center of mass is equal to m times g times the arm, which is d times sinus theta. So we remember from our previous discussions of the rotation of rigid bodies that net torque acting on the rigid body with respect to some point about which the system can rotate will be equal to moment of inertia of this body with respect to that point times angular acceleration alpha. So we also remember that angular velocity is first derivative of theta over time, and angular acceleration is the second derivative of theta over time. So now we can write the following. We can write that taking into account that this torque, similar to the tangent force for simple pendulum, always tries to move the system into equilibrium condition. Then we can put minus here, mg times d sinus theta, and that will be equal to a moment of inertia I times d square theta over dt square. So we can rearrange it and also get rid of any coefficient next to second derivative. So it will be d square theta divided by dt square plus mg times d divided by I times sinus theta, and that is equal to 0. So now again we consider the fact that we perform all this periodic motion with theta quite small, so theta less than 0.2 radians, and in this case sinus theta can be replaced by theta with some level of accuracy. So we will have final differential equation for this periodic motion of a physical pendulum, d squared theta times dt squared plus m times g times d divided by I times, instead of sinus theta, we have theta. That's equal to 0. So as you see, we have the same type of differential equation as two previous for the system spring block and is a simple pendulum. However, here we have different coefficient, and means that eventually we get this form of equation for theta as a function of time will be theta maximum times cosine omega t plus p. But in this case, for the physical pendulum, we can write that omega is equal to square root of mg times d divided by moment of inertia I. And the period of such periodic motion of physical pendulum will be 2 pi divided by omega equal to 2 pi square root of moment of inertia divided by mg times d. What is nice about this equation that we also can measure quite accurately the period of physical pendulum. If, for instance, we have a system with known position of the center of mass, and then we can easily measure this distance between the center of mass and the point about which rotation is happening. Then we know the total mass, we know the distance between center of mass and this point. We know period because we can measure it experimentally. So we can determine, calculate moment of inertia of our physical pendulum of any shape rigid body with respect to this point O about which the physical pendulum can rotate. So that could be quite useful approach. If we know position of the center of mass, we don't need to run complicated calculations to get the moment of inertia. With respect to some point, we can just make physical pendulum of this rigid body and experimentally determine moment of inertia with respect to this specific point of our choice. So that could be quite convenient. So summarizing our discussion today, we considered the total mechanical energy of simple harmonic oscillator. On the example of string block system, ideal without any friction and dissipation of energy, we have shown that total mechanical energy is a constant, and that is equal to, so it doesn't change with over time, and that's equal to the potential energy of the string at the maximum displacement, which is the amplitude value. So which can be used to determine velocity as a function of displacement of a simple harmonic oscillator. Also, we considered two new important systems in the scope of this simple harmonic motion, which is simple and physical pendulum. We derived equations for differentials, equations for their motion. We have shown that these differential equations have the same form as differential equation for the string block system. And obviously they have the same form of the solution while we operate with displacement in the string block system and angles when we deal with pendulum. So that is the general summary of our today's discussion. Next discussion, which, as I mentioned earlier, will be on Sunday. I will send you the time and link to the Zoom meeting soon. We will discuss simple harmonic oscillation in the case of some drag force acting on the block attached to the string. So it's so-called damping of simple harmonic motion. So that will be our next topic. And now if you have any questions, you are welcome to ask. Okay, guys, if everything was clear, then thank you for your attention and see you on our next discussion. Take
Okay,
care
thank you.
and have a good day. Bye-bye.
Thank you. Bye-bye.
Yeah, you too.
Thank you. Bye.
Thank you. Goodbye.
Thank you. Goodbye.
Bye.
Thank you for the lecture. But
You're welcome.
can you show, please, the second slide we had today?
Sure, 1 second.
I just forgot what I should write at it.
So you mean which exactly?
It's a bit older. Older.
Okay. Yes. So you mean for
Yeah,
slide?
I mean that. I
Uh-huh.
just print screen. Thank you.
No problem. And keep in mind that we have this all available online, so you can double check if you need.
I'm visiting the folder for students with solutions of 2 midterms and physics full manual, but I did not found any of that slides. Maybe it's
you
another.
mean, okay, sure. It was in this this link to the to recorded videos of our discussions is in this welcome email which I sent to all of you guys at the beginning. There is,
Okay.
yeah, so you can double check that one.
Thank you again.
You're
very much.
welcome. Take care and have a good day. Bye-bye.
Goodbye.